All right, this next video is going to talk about the second derivative test and local max and local mins, both of which are going to reflect what you learned in Calculus 1 regarding them. So for this first definition, so we're going to let our function be a two-variable function, which is continuous, which was necessary before, and an open set containing the point x naught, y naught. So we have a local maximum if our function at that point is greater than or equal to all functions with any xy points in a disk, some disk centered at this x naught, y naught. So if we take any smaller and smaller disk centered there, our smallest value in the area, or I guess our largest value in the area, will be this function at x naught, y naught. That's when we have a local maximum. If this holds for all points in the function, then it's global maximum. Another term for that is absolute max, which is probably what you would have heard back in Calculus 1. That's typical term for that. And the local min works the same way. So if your function at that x naught, y naught is less than or equal to all other values in that disk around it, then you have a local minimum, and it's a global or absolute minimum if it's smaller than all other value of x, y that you can put in there. All right, Fermat's theorem is below, and essentially we've got the same function, or a two-variable function. It's got to be continuous in an open set containing the point x naught, y naught, and we have to know that the partial derivatives both exist. So the partial derivative with respect to x and y each exist at the point x naught, y naught. Then, so if f has a local extreme at this x naught, then it's a critical point. So if it's a local extreme, then it's a critical point. All right. So the second derivative test is going to work in a very similar fashion to what you would have learned in Calculus 1. First of all, we're finding the second derivative, and this is what we're doing here. We're calculating this d and using the second derivative with respect to x at the point, multiplying it by the second derivative with respect to y at the same point, and then we're subtracting the squared of the derivative of fxy. We're squaring that point. Okay, pink is a little dark. We'll go back to green. So if that d is strictly positive, in both of these cases it's strictly positive, we're going to have some sort of local extrema. The other thing we have to check is the partial derivative, second derivative with respect to x. If that's greater than 0, we have a local minimum. If that's less than 0, we have a local maximum, and that's going to coincide with what you learned about the second derivative test back in Calc 1. This number 3 here, if we find that derivative above d is strictly negative, then we have a saddle point. So an illustration of a saddle point is where that line points in that third graph over there. It's a stable point, and it's neither a maximum nor a minimum. And the picture they gave us here looks kind of like a saddle. I guess it can just kind of rest on that point, and the graph is at an equilibrium. These other ones, here's two local min points on this graph here. One of those is likely to be a global or extreme min. Similarly, local max on these. All right, so our problem, we're looking for critical points of the function using algebraic techniques. We're going to complete the square. and then verify using a partial derivative test. We're going to do the second derivative test above. But first, let's do the complete the square stuff. And they gave us negative values, which makes it a little trickier, but I'm going to pair up the x's and the y's. So negative x squared plus 8x. And that's one group. And then I've got negative 5y squared minus 10y. And I've got this negative 13 on the outside here. All right, I'm going to pull out a negative 1. And so I'm left with negative 8. Negative 8 divided by 2 is going to be negative 4. Square that, it's 16. So it's going to be x minus 8x plus 16 minus 16. So that first 16 is going to go towards squaring that. And the second one, we're going to distribute with the negative and pull it out. I'm going to pull out a negative 5y here, or negative 5, excuse me. And that means I'm left with y squared, and this should be an x squared, plus 2y. So 2 divided by 2 is 1, 1 squared is 1, so I'm going to both add 1 and subtract 1 from this group. And now let's do the squaring and distributing the negatives. So it's negative x squared minus 4. And then negative times negative 16 is plus 16. Negative 5 times the quantity y plus 1 squared. And then negative 5 times negative 1 is positive 5. Scroll down just a little bit here. Okay. And this ultimately gives us and what do we have here? Positive 8 is what we have left. So this is our function that they want us to deal with, and we're going to need to find our derivatives here. So let's find the partial derivatives first here. So using this derivative with respect to x equals, oh, I messed up that last bit here. Hold on. Square doesn't go there. Square goes here. Apologies. Okay, so the derivative with respect to x, we have negative 2 times quantity x minus 4 just to the 1. The derivative of x is 1, so we're done. And then the second derivative of that is, let's see, is going to equal just negative 2. The first derivative with respect to y is going to equal, our second one, we're looking, negative 5 times 2 is negative 10. And then the quantity is y plus 1. And that means our second derivative is negative 10. Okay, so we need a couple things here. We need this d. Notice either one I take, either if I'm looking at f, x, y, I'm going to get 0 because it's all in respect of the given function, and I take the derivative of that with respect to the other one, and I get 0. So we have to note that equals 0. So our d is going to be negative 2 times negative 10 plus 0 quantity squared, which gives us 20, and that is greater than 0. So let's scroll up a little bit. So we have it greater than 0, so we have to determine if our second derivative with respect to x is positive or negative, and it is in fact equal to negative 2, which is negative. So because of that, we have a local maximum. And we want to find the points Well, we know the other the points is 4, 1, so I guess that works. 4, -1. So point is 4 and -1 from our factoring above, and we have again, this is so fxx equals -2, which is less than 0, which implies, as we can see above, let me highlight that again, less than 0 is going to be a local maximum. Local max, and it's going to be at the points 4 and -1. And that's the critical point we found.